Welcome! In this video, we are going to learn about subfunctors, sieves, and cosieves slowly and gently. If these words feel large right now, that is completely normal. We will build the meaning one small picture at a time. The main theme is simple. A subfunctor is a consistent way of choosing smaller pieces inside a functor. Sieves and cosieves are two special ways this idea appears when arrows point into, or out of, one fixed object. Let us start with the basic setting, a category. A category is a world made of objects and arrows. The objects might be called X, Y, and Z. The arrows tell us how to move from one object to another. The important extra feature is composition. If an arrow G goes from Y to X, and an arrow F goes from X to C, then we can follow G and then F. The combined arrow goes from Y all the way to C. A functor is like a translator between worlds. Here the functor F takes the category C and translates it into set, the category of sets and functions. Each object becomes a set. Each arrow becomes a function between sets. The key promise is that the translation respects structure, so the shape of the arrow world is carried into the shape of the set world. Now we separate two kinds of translation. A covariant functor preserves the direction of arrows. If G goes from X to Y, then f of G goes from f of X to f of Y. A contravariant functor reverses direction. The arrow in the category may point one way, while the function between sets points the other way. This reversal is the source of the difference between sieves and cosieves. A subfunctor is a smaller functor living inside a bigger functor. If the larger functor F assigns a set to each object, then the smaller functor G assigns a subset at each object. But this is not just choosing random subsets. The choices must be stable under the functions supplied by the functor. In everyday language, once an element has been selected, the functor's motion must not throw it outside the selected world. Before we focus on sieves and cosieves, the slides pause for a universal definition. This is the most abstract version. Do not worry if it feels formal. The goal is to see the big shape first, and then we will come back down to sets, arrows, and diagrams. Think of this section as naming the principle that all the later pictures are illustrating. In the most general definition, a subfunctor is a subobject inside a functor category. That sentence is compact, so let us unpack it. First, we build a category whose objects are functors. Then saying that one functor is a subfunctor of another means that, inside this new category, one object sits inside another. It is the same familiar idea of inclusion, lifted up one level. Here is the formal statement. A subfunctor of a functor G from C to D is a pair. The pair consists of another functor F and a natural transformation I from F to G. The important condition is that each component I at an object M is monic. In simpler language, every piece of F embeds into the corresponding piece of G, and those embeddings fit together naturally. What does monic mean? In ordinary set language, a monomorphism behaves like an injection. It puts one thing into another without collapsing two different elements into one. So when the target category is set, a monic map from F of M to G of M lets us safely think of F of M as sitting inside G of M. This is the technical bridge from abstract inclusion to ordinary subsets. At the functor category level, we treat whole functors as objects. The symbol bracket C, D means the category of functors from C to D. Inside that category, a subfunctor is represented by a monomorphism from one functor into another. This is a high-altitude view. The next slide zooms in to show what this means object by object. When we look inside a natural transformation, we see one component map for every object. For each arrow F from M to N in C, the two paths around the square must agree. Going across with F and then down by inclusion must give the same result as going down by inclusion and then across with G. That is what the word natural is doing here. It means the inclusions respect all the arrows. Now we bridge back to the rest of the guide. When the target category is set, monomorphisms are simply injective functions. Up to the usual harmless identification, that means f of m can be treated as a subset of g of m. In the coming slides, S will select subsets of Hom sets. The same commuting square becomes the blueprint for Sieves and Cosieves. We now enter Part 1, Contravariant Functors and Sieves. This is the side where arrows are read backwards by the functor. If that sounds strange, stay with the diagrams. The picture to keep in mind is arrows pointing into a fixed object C, and approved arrows staying approved when we attach more arrows before them. The roadmap is this. Contravariance reverses arrows, and that reversal creates closure under composing on the right. If F goes from X to C, and G goes from Y to X, then the composite F after G goes from Y to C. A sieve is exactly a collection of arrows into C that is closed under this operation. Once an arrow into C is accepted, every longer route into it is accepted too. Here is the general definition of a contravariant subfunctor. We have a contravariant functor F from C to set, and another contravariant functor G. For G to be a subfunctor of F, two things must hold. First, at every object, G chooses a subset of F. Second, every arrow action of G is just the corresponding arrow action of F, but restricted to the smaller chosen subset. The domain changes because the functor is contravariant. If the original arrow F goes from C' to C, then F reverses it into a function from f of C to f of C'. The smaller function g of f must do exactly the same thing, but only for elements that already live inside g of C. This is the stability condition, written carefully. In this diagram, the category C is on the left and set is on the right. Notice the reversal. The arrow in C points one way, while the corresponding functions between sets pull the selected data the other way. The purple sets are the smaller chosen parts. The message is that the smaller action G of F is not new. It is the big action F of F, restricted to the purple world. The one-object category is a tiny example, and tiny examples are very useful. There is only one object and only its identity arrow. A functor sends that object to a set A and sends the identity arrow to the identity function on A. A subfunctor simply chooses a subset T of A, and the identity restricts to the identity on T. So here, subfunctors are exactly subsets. Now we introduce the contravariant Hom-Functor. Fix an object C. The functor H sub C sends each object X to the set of all arrows from X into C. If we have an arrow G from Y to X, then H sub C sends it to a function that takes an arrow F from X to C and returns the composite F after G, an arrow from Y to C. This is precomposition. Precomposition simply means attaching something on the input side. Start with an arrow F from X to C. If another arrow G lands in X going from Y to X, then we can place G before F. The result is F after G, a longer arrow from Y to C. This is the core move behind a sieve. This diagram shows the Hom-Functor as a pullback operation. In C, we have an arrow F into C, and an earlier arrow G that leads into the domain of F. In set, the function sends F to F after G, so data is pulled backward along G. The word pullback here is intuitive. The arrow into C gets pulled back to a longer arrow into C. Now suppose S is a subfunctor of H sub C. At the object level, this means that for every object X, S of X is a subset of Hom from X to C. The full Hom set is the bag of all arrows from X into C. The subfunctor S chooses a smaller bag of approved arrows. But again, the choices must be consistent with the arrow action. The bags within bags picture makes the object-level idea visual. The large bag is the full Hom set, every arrow from X to C. The purple bag is S of X, the selected part. Some arrows are approved and sit inside the purple bag. Other arrows are rejected and remain outside. By itself, this is only a subset choice. The next slide adds the crucial closure rule. At the arrow level, the mapping S of G must be the same as H sub C of G, but restricted to the selected subset. Since H sub C of G means precomposition by G, S of G also means precomposition by G. The safety condition says, if you start with an approved arrow in S of X, then after composing with any arrow G from Y to X, the result must land in S of Y. Here is the contravariant commutative square. The top path acts inside the smaller selected sets. The bottom path acts inside the full Hom sets. The vertical arrows are inclusions. The square says the top operation is just the bottom operation with the domain and codomain restricted. This is the formal version of consistency. Now the square reveals the sieve rule. Pick an approved element F in S of X. That means F is an arrow from X to C that has been selected. If G is any arrow from Y to X, then S of G sends F to F after G. Because S is a subfunctor, that result must be in S of Y. So approved arrows into C stay approved after precomposition. This is the definition of a sieve. A sieve S on an object C is a collection of arrows whose codomain is C. The closure condition is the heart of the definition. If F from X to C belongs to S, and G from Y to X is any arrow, then the composite F after G must also belong to S. A sieve accepts all earlier extensions of its accepted arrows. Why is it called a right ideal? In the composite F after G, the arrow already in the sieve is F, and the arbitrary arrow G is composed on the right side of F. So closure means, whenever F is in S, every composite F after G is also in S, whenever the composition makes sense. The word right is about the side on which the new arrow is attached. The funnel diagram gives the intuition. Once an arrow into C is approved, every incoming way of reaching its domain is also captured. You can think of the sieve as accepting not only a route into C, but all longer routes that flow through that route. Nothing needs to be reapproved one by one. Closure forces the whole family of composites to be included. We can now say the main theorem of Part 1 in beginner language. A sieve on C is exactly a subfunctor of H sub C. the contravariant Hom-Functor Hom from blank to C. The subfunctor data gives subsets of Hom sets. The Sieve closure says those subsets are stable under precomposition. These are not two different ideas. They are the same idea in two languages. Here is a practical checklist. To test whether a collection S is a sieve on C, ask 3 questions. First, does every arrow in S end at C? Second, if an arrow F into C is in S, can we precompose it with every arrow that lands in its domain? Third, are all those composites still in S? If the answer is yes, you have a sieve, and equivalently a contravariant subfunctor of H sub C. We now move to part 2, covariant functors and cosieves. This is the dual story. Dual means that the same pattern appears with arrows reversed. For cosieves, the arrows begin at the fixed object C and move outward. Instead of pulling accepted arrows backward, we push accepted arrows forward. The roadmap for cosieves is the mirror image of the sieve story. Covariance preserves direction. If F goes from C to X and G goes from X to Y, then the composite G after F goes from C to Y. A cosieve is a collection of arrows out of C that is closed under this operation. Once an outgoing arrow is approved, every continuation after it is approved too. For a covariant subfunctor, the direction is not reversed. We have a covariant functor F from C to set, and a covariant functor G. At every object X, G of X is a subset of F of X. For every arrow G from X to Y, the function G of G is the restriction of F of G to the smaller domain G of X. The smaller functor follows the same motion as the bigger one. This diagram shows the covariant case. The arrow G points downward in the category C, and the functions F of G and G of G also push downward in set. The purple subset at X is carried into the purple subset at Y. Again, G of G is not a separate invention. It is F of G, restricted to the selected parts. Now we define the covariant Hom-Functor. Fix the same object C. This time, H superscript C sends an object X to Hom from C to X, the set of all arrows going out of C into X. If G goes from X to Y, the functor sends an arrow F from C to X to the composite G after F, an arrow from C to Y. This is post-composition. Post-composition means attaching something on the output side. Start with an arrow F from C to X. If an arrow G leaves X and goes to Y, we place G after F. The result is G after F, a longer outbound route from C to Y. This is the core move behind a cosieve. Here the Hom-Functor acts as a push forward. The direction in C and the direction in set match. An outbound arrow from C to X is pushed along G to become an outbound arrow from C to Y. If sieves felt like pulling arrows backward into C, cosieves feel like pushing arrows forward away from C. Let S be a subfunctor of the covariant Hom-Functor H superscript C. At the object level, S of X is a subset of Hom from C to X. The full Hom set contains all possible outbound paths from C to X. The subfunctor selects a smaller set of approved outbound paths. We still need these selected paths to behave consistently under post-composition. This filtering diagram is the outbound version of bags within bags. The large set contains all arrows from C to X. The purple subset contains the arrows approved by S. Some arrows are in and some are out. But a cosieve is more than a list of approved arrows. It must also approve every forward continuation of an approved arrow. At the arrow level, S of G must be the same as H superscript C of G, but restricted to S of X. Since H superscript C of G means post-composition by G, S of G also means post-composition by G. The safety condition is this. If an outbound arrow has been approved, then after composing it with any arrow that continues outward, the new outbound arrow is still approved. The covariant commutative square expresses that same rule formally. The top path pushes approved arrows forward inside the smaller selected sets. The bottom path pushes all arrows forward inside the full Hom sets. The inclusions connect the small world to the large world. The square says the small push forward is exactly the large push forward restricted to approved arrows. The square is already the Cosieve rule. Pick an approved element F in S of X. That means F is an arrow from C to X. If G is any arrow from X to Y, then S of G sends F to G after F. Since S is a subfunctor, the result must be in S of Y. So approved arrows out of C stay approved after post-composition. This is the definition of a cosieve. A cosieve S on an object C is a collection of arrows whose domain is C. If F from C to X belongs to S, and G from X to Y is any arrow, then the composite G after F must also belong to S. In plain words, a cosieve accepts every possible continuation of an accepted outgoing arrow. Why is it called a left ideal? In the composite G after F, the new arbitrary arrow G is placed on the left side of F. The arrow F is already in the cosieve, and we close under composing another arrow after it. So the left side of the notation is where the new piece appears. The expanding web picture captures the feeling of a cosieve. Once an arrow leaves C through an approved path, every further path that continues from there is also captured. Instead of a funnel into C, we have an expanding network out of C. The collection grows forward along every possible continuation. The main statement of Part 2 now matches Part 1 perfectly. A cosieve on C is exactly a subfunctor of H superscript C, the covariant Hom-Functor Hom from C to blank. The subfunctor data gives selected outbound Hom sets. The cosieve closure says those selections are stable under post-composition. Again, two languages describe the same structure. Here is the cosieve checklist. First, does every arrow in S start at C? Second, if F from C to X is in S, can you post-compose it with every arrow G from X to Y? Third, are all the composites G after F still in S? If yes, then you have a cosieve. Equivalently, you have a covariant subfunctor of H superscript C. We have reached the final duality and recap. At this point, the vocabulary may still feel new, but the pattern should feel familiar. A subfunctor is a consistent selection. A sieve is the contravariant into C version. A cosieve is the covariant out of C version. Now we place the two side by side. Here is the comparison. A sieve is a subfunctor of Hom from blank to C, so its arrows point into C. It is contravariant and closed under precomposition. A cosieve is a subfunctor of Hom from C to blank, so its arrows point out of C. It is covariant and closed under post-composition. The two definitions are mirror images. The final conclusion is that contravariant subfunctors of the incoming Hom-Functor are sieves, or right ideals. They behave like funnels. Once an arrow into C is selected, all earlier routes feeding into it are selected. Covariant subfunctors of the outgoing Hom-Functor are Cosieves, or left ideals. They behave like expanding webs. Once an arrow leaves C through the selection, all later continuations are selected. These memory aids are meant to stay with you. For a sieve, think: if the last arrow into C is approved, then all longer routes into C through it are approved. For a cosieve, think: if the first arrow out of C is approved, then all longer routes continuing from it are approved. Last arrow in, first arrow out. That is the whole contrast. The glossary collects the symbols. C is the category we are studying. Set is the category of sets and functions. The object C is fixed. The letters X and Y vary. The Hom expression from blank to C means arrows into C. The Hom expression from C to blank means arrows out of C. S is the selected subfunctor, Sieve or Cosieve, depending on context. The final map summarizes the entire journey. Start with a subfunctor of a Hom-Functor, a consistent choice of smaller sets. If the functor pulls back along arrows, we are in the contravariant world and the structure is a sieve. If the functor pushes forward along arrows, we are in the covariant world and the structure is a cosieve. Same idea, different direction. Thank you for going slowly through it.